Hello students, in last session we have seen the introduction about refrigeration. In this session we are going to see unit of refrigeration and COP. COP is nothing but coefficient of performance. It is also one of the important calculation that we are going to do in almost all topics. Coming to the topics in this unit, already we have seen introduction to refrigeration, unit of refrigeration, COP, ideal cycles, refrigerants desirable properties, refrigerants classification, refrigerants nomenclature. So these are the topics in first unit. We have seen introduction to refrigeration and now we are going to see unit of refrigeration COP. In next session we are going to start ideal cycles, refrigeration cycles. In under this topic we are going to see different operating cycles, theoretical cycles as well as actual cycles we are going to discuss in this topic. Refrigerants desirable properties, refrigerant nomenclature and classification, both we are going to discuss in one session. That is the plan to complete our first unit, students. Coming to our second topic in this unit, it is unit of refrigeration. Refrigeration is the process of removing heat from a space or substance to lower its temperature. The temperature is lowered in such a way that the heat is removed from either space or from substance. So that is nothing but refrigeration process. The effectiveness of refrigeration system is measured in terms of unit of refrigeration, which quantifies the rate at which heat is removed. So this is a simple definition of unit of refrigeration, or it is refrigeration process. Definition of unit of refrigeration, it is as simple as this. The unit of refrigeration is defined as the amount of heat energy absorbed or removed in a refrigeration system per unit time. Per unit time, it is nothing but during a particular period of time. The most commonly used unit is the ton of refrigeration. In short, it is known as TR. We are going to see this TR everywhere in our calculations. There are so many numerical problems that we are going to solve. In that, we are going to see this tonnage calculations. This ton of refrigeration is also defined like this. It is defined as the amount of heat absorbed to completely freeze 1 ton. 1 ton, it is equal to 2000 lbs. It is in terms of pounds of pure water at 0 degrees Celsius in 24 hours. So this is the ton of refrigeration definition. So we are going to completely remove, or we are going to freeze 1 ton of water at 0 degrees Celsius in 24 hours time. That is known as 1 ton of refrigeration. That is why the 1 ton water is considered to remove heat in such a way that it should become ice into solid. So that is the 1 ton of refrigeration, students. Let me give units in terms of many parameters, and you should remember all these units, students. Unit of refrigeration in SI units, 1 ton of refrigeration equal to 3.517 kilowatts. So this is very important number, you should remember. And 1 ton of refrigeration equal to 12,000 BTU. It is in terms of British thermal units per hour, and this is not SI unit. We are not going to use this particular unit BTU. Or 1 ton of refrigeration equal to 211 kilojoules per minute. So this is another number you should remember, students. Other units of refrigeration You can see here 1 ton. This is same 3.1517 kilowatt. 1 ton of refrigeration equal to 211 kilojoules per minute, and 1 ton of refrigeration equal to 12,000 BTU per hour. 1 kilowatt. So in terms of kilowatt, we can say it is 0.287. So we are converting vice versa. 1 kilojoules per second equal to 0.284 ton of refrigeration. 1 kilocalorie per hour is equal to 0.001163 kilowatt. These are the numbers. Try to remember, and these values will be very handy in solving problems, students. So don't forget this. Make a note and memorize these values. These are very useful values we are going to use in solving problems. We see a small mathematical derivation here. It is very simple, and also it will be very useful if you understand while solving our problem, students. Mathematical derivation of 1 ton of refrigeration. We assume that 1 ton of water, it is 2000 lbs, is to be frozen completely at 0 degrees Celsius in 24 hours. That is nothing but 1 ton of refrigeration. The latent heat of fusion of ice is equal to 335 kilojoules per kg. And please remember this value also. Students, the latent heat is nothing but the amount of heat required to convert 1 gram of ice into water. So we are just melting the ice into water. So that is nothing but latent heat of fusion of ice, and 1 gram we are converting into water at 0 degrees Celsius without change in temperature, students. That is very important. Mass of 1 ton is equal to 2000 lbs. It is equal to 907 kg. 1 kg equal to 2.20462 lbs. Suppose if you get any question in terms of lbs in exam, you should not say that you don't know the values. You should remember 1 kg equal to 2.20462 lbs, or you can remember 2.205 directly. So 3 numbers after decimal place will be sufficient. You can remember 2.205 lbs equal to 1 kg. So heat removed per day. Here the Q is the heat removed equal to mass into latent heat. So mass is equal to 2000 lbs or 907 kg. Let us take 907 kg, and latent heat of fusion 335 kilojoules per kg equal to 907 kg into 335 kilojoules per kg. It comes 303.845 kilojoules. So this is the heat removed per day. Heat removed per second. So we can convert this to second. So instead of day, we can convert this into second. Before converting into second, we have to convert into hours, and then we have to convert into minutes, and then we have to convert into seconds. So it can be done 24 hours, 60 minutes, 60 seconds equal to 86,400 seconds. So this much seconds we have per day. So it is 303.83845 divided by 86,400 seconds equal to 3.517 kilowatt. So we are converting into kilowatts. So that is Q per second. So that is heat removed per second is equal to 3.517. So here this is nothing but 1 ton of refrigeration equal to 3.517 kilowatt. So this value also you please remember, it will be very handy. That's why in previous slide I have given you all the values. 1 ton equal to, in terms of different units I have given you. So please remember all these values. Next we see coefficient of performance. Next topic in this unit is COP. It is nothing but coefficient of performance. Definition of COP, it is as simple as this. It is the coefficient of performance is a measure of the efficiency of a refrigeration or heat pump system. It is defined as the ratio of the desired effect. It may be cooling or it may be heating to the input work. So it is the ratio of Q by W. In terms of Q can be in both ways. It can be heat supplied or it can be heat removed in case of refrigeration system. In case of a heat pump system, it is nothing but heat supplied. So COP is equal to useful refrigeration effect divided by work input. It is theoretical COP equal to Q by W, and COP for refrigeration system, it is QC by W. QC is nothing but the cooling effect, refrigeration effect, and W equal to work input. And similarly for heat pump, it is QH by W, and QH is nothing but heat supplied to the system, and work W is same as the work input to the heat pump. So this is about coefficient of performance and its equations for heat pump as well as refrigeration system. So coefficient of performance per unit mass, COP equal to Q by W, and the coefficient of performance is the reciprocal of the efficiency. So coefficient of performance is reciprocal to of the efficiency of a heat engine. It is always greater than unity. It is greater than 1 always. And the ratio of the actual COP to the theoretical COP is known as the relative coefficient of performance, and this is mathematically actual COP divided by theoretical COP. It is known as relative COP. Relative COP also we are going to calculate in our numerical problem, students. Relation between COP of refrigeration and heat pump, it is always COP of heat pump equal to COP of refrigerator plus 1. This shows that heat pump is always more efficient than a refrigerator when working between the same temperature limits. Factors affecting COP: operating temperatures. Higher temperature differences reduce COP, and refrigerator properties. The refrigerant properties, efficient refrigerants provide higher COP. So in next session we are going to see about refrigerants also, and we are going to discuss which one is suitable for which application, and we are going to discuss in detail. Compressor efficiency. Compressor is one of the major component of a refrigerator system. Well designed compressors improve system COP. Heat exchanger effectiveness. The proper condenser and evaporator design enhances COP. Definitely a proper condenser and evaporator is required to enhance COP or to achieve more COP. Expansion valve. Expansion valve is also one of the important element in refrigerator system. Reducing expansion losses helps improve COP. It is the another advantage here. When the reducing expansion valve losses, so we have to have these losses at minimum level. So once we have these losses at minimum level, definitely COP will improve. We see the applications of COP in refrigeration and HVAC systems. These are very simple applications. Evaluating energy efficiency of refrigerators and air conditioners, optimizing heat pump performance in buildings, designing eco-friendly refrigeration systems, comparing different refrigerants based on performance, and these are the four major applications COP in refrigeration and HVAC. The coefficient of performance is a crucial metric in refrigeration and heat pump systems. A higher COP indicates greater efficiency. So always COP, when it is higher in its value, then we have more advantages and it will be more effective. The refrigeration system is more effective in this case. By optimizing system parameters, energy consumption can be minimized, leading to cost-effective and eco-friendly cooling and heating solutions. So by optimizing all these parameters, we can get so many advantages like cost-effective, eco-friendly cooling systems, and power consumption will be lesser. These are the advantages. So we see a few numerical problems, very simple numerical problems only. When we start our ideal cycles, there we are going to have so many numerical problems where they are all little tedious problems. If you have good practice students, they are nothing, very simple problems. You can easily solve those problems. We will see only a 2-mark range problems here. Problem 1, it is a refrigeration system has a capacity of 5 ton of refrigeration. Convert this value into kilowatts. So kilowatts, we know how to convert it. And this is 1 ton of refrigeration equal to 3.517 kilowatt. That's why you should remember these values, students. And 5 ton of refrigeration equal to 5 into 3.517 equal to 17.587 kilowatt. So as simple as this, 5 into 3.517 will gives you the kilowatt equal to 5 ton of refrigeration. So next problem, find the COP of a refrigeration system if the work input is 80 kilojoules per kg and refrigeration effect produced is 160 kilojoules per kg of refrigerant flowing. So it is again a very simple problem. The work input is given and the unit of refrigeration is given and tons of refrigeration is given. So we can easily calculate this. Solution is here W, that is the work input, is 80 kilojoules per kg and Q is 160 kilojoules per kg. And COP is equal to Q by W. So Q by W 160 by 80 equal to 2. So 2 is the coefficient of performance for this particular refrigeration system. We see one more problem on this. Cooling load calculations, that is tonnage calculation. And a cold storage plant removes 7,20,000 kilojoules of heat per hour. So it is 7,20,000 kilojoules per hour. Calculate its refrigeration capacity in TR. So that is ton of refrigeration. 1 ton of refrigeration equal to 211 kilojoules per minute. Here it is given 7,20,000 kilojoules per hour. So we have to convert this into minutes immediately. And now 7,20,000 kilojoules per hour. If I divide by 60, I will get 12,000 kilojoules per minute. How tonnage I can calculate? It is 12,000 kilojoules per minute divided by 211 kilojoules per minute. So equal to 56.87 ton of refrigeration. So this is the answer. Answer is 56.87 ton of refrigeration. It is again very simple problem. We see another problem. Next problem. Work done in refrigeration system. So we are going to calculate the work Q by W, that is the denominator term we are going to calculate here. A refrigeration system operates with a COP of 4.5. So COP is given directly and it provides a cooling effect of 10 kilowatts. So cooling effect is 10 kilowatt. So that is Q. Find the power input required. So here we know COP, we know the input, that is the cooling effect Q, that is 10 kilowatt. It is COP equal to refrigeration effect divided by work input, that is Q by W, and here 4.5 equal to 10 by W, so W equal to 10 by 4.5, so that is 2.22 kilowatt. So this is the answer, that is the work done we are calculating in this particular problem. Again, these are all just 2 mark questions only, but remember these will be very handy while solving the TDS problems that we are going to commence in next class. So one more problem we'll see here, cooling effect of a refrigerator. So here we are going to calculate Q value. A refrigerator extracts heat at a rate of 8000 kilojoules per hour. Find its equivalent TR value. So 1 TR equal to 211 kilojoules per minute. It is given 8000 kilojoules per hour. So this should be converted into minute, kilojoules per minute. So here 8000 kilojoules per hour, 8000 divided by 60 equal to 133.33 kilojoules per minute. So TR is equal to 133.33 divided by 211 equal to 0.632 TR, that is ton of refrigeration. Answer is 0.632 ton of refrigeration. A simple question, and these are all the types, and where whatever parameter, 2 parameters will be known parameters, 1 parameter will be unknown parameter. So that accordingly you have to calculate, students. You have to be little careful, and the formulas are straightforward, so you have to remember the simple formula and with which you can calculate all this. We stop here, and coming to reference books, these are the books Rajput and Arora, and I felt Kurmi is a very handy book. You can refer this fifth reference book, and I have taken almost all the problems from Kurmi book as well as Rajput. CP Arora is also good book, and I am referring this book also, students. We have NPTEL course. When you go to this course, you can download a lot of material, that is also very useful. And one more, brighthubengineering.com/HVAC, it gives the preliminary information, and that will be very handy and useful, students. You can refer that. We stop here. Thank you, students. Once again we meet in next session in a very short while. Thank you, students.